Good morning. Hello, everyone. Welcome to MACSMIN 2026. It's a pleasure to introduce Professor Saulius Grazulis from Vilnus, right, who will talk about crystallography open database. So over to you, please.
Okay, good morning, everyone. And I wish to thank organizers and especially Vitaly for this kind invitation and the possibility to share our insights and results with this audience. And since I have a generous allocation of time, I decided that I not only speak about the topic that was announced, but show you how we are moving towards this goal. And on the way, I will expose our data sources, our tools that we use, with the hope that they will be useful maybe for some of your investigations. So my talk will be organized as follows. I will talk about the crystallography open database a little bit, present the tools to access data from that database which we use. Then I will give some illustrative uses of the code, which actually are a path towards the nets and knots that we want to eventually have cataloged, along with atomic radii investigations. Then I will discuss what we're doing on nets and knots, and then I will talk a little bit about how I imagine scientific software could be written and used as a way of communicating science, not only just doing some calculations. So let's start on the first part. So as many of you probably possibly have already encountered, the crystallography open database is the currently largest open access collection of crystal structures, which includes small molecule crystal structures, minerals, organic and metal organic compounds. So basically anything that is not covered in the open databases, PDB and nucleic acid databases and related ones. COD is not the only database that we co-develop. We have also a theoretical crystal structure database together with colleagues, or rather we help our colleagues in Mexico. We started doing this with colleagues in Mexico who now develop the material properties database. I think it's a very valuable resource with experimental material properties data. We have predicted crystal structures, and even we have Raman spectra, all distributed under similar licenses and in similar way. But of course, for our topic today, the COD is the most interesting and relevant database. You can access crystallography open database in multiple ways. Start with the most easy point-and-click interface, the web page, which has URL on the top, which allows you to search and view individual structures. But then if you want more data, you can use our REST API, or very advised, you can, very much recommended, you can use the Optimate API, which is a standardized and standard for sharing material science data developed by a consortium of database maintainers and implemented by, I think, over a dozen now of most prominent material science databases. There is a standard publication on that. You can also directly access our SQL server. And of course, if you want to do massive computations, the best thing is to download the code to your computer. And since it's an open access database, the license is CC0, you are free to distribute it wherever you want, give it to students, colleagues, put on your computing nodes and do your research with it. I don't need to introduce CIF much in this audience. It was already presented yesterday. So we use this standard maintained by the IUCR to record, ingest, and distribute all our data. And yeah, as you've seen already, this is an example of it. Now, the CIF has enormous advantage, and that is a standard, and that is actively developed and maintained. But it is a quite complicated standard, therefore even though it's a text file, you cannot simply read it into a program and use simple splitting to get data out, even though people sometimes try to do that. You need a full correct parser for this file. Multiple parsers are implemented, and we have one which we use for our purposes with a peculiarity that it not only recognizes corrected files, but can correct some mistype or misformed ones, which is very important when you ingest data into a database. So, for example, if quotes are missing or the data name is not provided in the input, then either you get a warning, of course, with a special option which says that you want to fix these mistakes. Otherwise, the software should not guess what the people meant. People should keep to the standard, and this should be an error. But with an option, you get a warning and you get correctly inserted quotes, essentially restoring the data. With this tool, we can guarantee that Crystallography Open Database has always correct syntax when you get it from us. Now, if you want to access distinct values in a CIF file, it is very tempting to use simple tools like grep or like maybe pandas in Python. Maybe you want to use Perl with simple splitting, and as said, this is not available for CIF directly. Therefore, we made it for ourselves and found that it's useful for our users, for the users of our database, to have simple tools that take CIFs and extract the requested data in a form of database query. CIF values is one of these tools which takes in the requested data names, the CIF files, and puts out a comma-separated value or tab-separated value GSV file. Both are standardized. We also can transform the whole CIF to a more complicated CSV file. And again, CSV and TSV files are supported by both utilities. And we also support actually a standard way to communicate data, ASCII delimited text, which for some reason is very seldomly used, but the standard is available since 70s or so. Basically, ASCII standard has special characters to delimit values and records in our output. And if we use them, we are just standard. Okay, so we support that as well. And this has an opportunity that it enables very simple parsing of the output, trivial parsing, and ensures that any value of the CIF can be encoded there. So you are safe analyzing data in this way. What can you do with this? Well, this is an example from one tutorial. You can then request structures, for example, of magnesium oxide in this case. And then Crystallography Open Database has not only structures, but also measurement conditions. So you can pick those structures that have pressure and temperature recorded, and voila, you have the equation of state. You can fit these multiple experiments published in different papers, and you can now see how the volume depends on pressure and temperature. Okay, and you see this is the room temperature, the most common value, but then there are a series of experiments which people did for dedicated conditions. To move further towards the nets, we need to somehow restore molecules, as we call it, or the correct name would be molecular entities, which means covalently connected sets of atoms, ions, maybe charged, maybe neutral. Because, as we know, covalent bonds are the ones that hold molecules together, and these are the most prominent interactions, the strongest interactions. So, for quite a while, we wanted to get a set of atomic radii from the open sources, from the open database like Crystallography Open Database, and it turned out that just filtering it by distance doesn't work very well. But what we did here in the recently accepted paper by Saulius Grazulis, who was her supervisor, and by the rest of our group, we partitioned the whole crystal structure into Voronoi cells. Okay, and then a lot of extra would-be contacts are filtered away. Voronoi tessellation turns out to be an excellent way to determine what the actual neighbors are. Okay, and then you have a very prominent gap between the short interactions, which we identify as covalent bonds, and then the non-bonded interactions and van der Waals and other interatomic interactions, or just neighbors. Between them, we have a van der Waals gap that can be determined automatically. Andres uses, and Saulius Grazulis, they use Gaussian mixture fit for that. And here you can have now the radii of different covalent bonds. This is how Voronoi tessellation actually looks. And here we can see why this works well, because these atoms would be connected. And maybe these atoms would be connected if you just use the distance cutoff, but in fact they are not, because they're, so to say, shielded by the benzene ring atom. And we use Kliment Olechnovich program Voronota, a very nice one. Although it's original paper that I cite here, it's updated to produce also a graphical output for JMOL now and for PyMOL. And with this tools, we now derived the set of radii, and it's well within the track of the known radii definitions. So nothing spectacular new here, but our contribution is that now we can automatically update these sets on unsupervised, on open data, and you can have the full provenance to the original measurements whenever you ask whether a covalent bond is here. And in some cases, this gives even better the results than the previous estimates. With these radii at hand, we now want to reconstruct molecules. And this turns out to be an important and a step that needs certain attention, I would say. And that's because, as you know, in crystal structures, we only have a so-called symmetric unit or a fundamental domain mathematically, if we define mathematically, of the crystal structure, to which we need apply the crystal symmetry operations. And we need to figure out which atoms are connected by covalent bonds using one of the radii set presented earlier. So we build a software called Topological, and actually where I started originally, this started as a student's master. Was it master? It was probably even the undergraduate BSc Bachelor of Science project, and turned out to be quite complicated and long and durable software. So originally we would just restore distinct molecules connected by covalent bonds, and I thought that's good enough. But of course, what you get from such crystal description, you of course get from a partial molecule here the full description through the symmetry reconstructed parts, but then, and you also get these molecules here and molecular entities. And you can have their compositions and their properties, but you don't know how many of these do you have in the crystal, nor in which ratios they are present, nor how they interact. So we can, of course, put them into one unit cell, but if you calculate the composition of the right unit cell, you see that it's wrong in red. Why so? Well, that's because some molecules are in a special position in many structures. That is, their symmetries coincide with crystal symmetries, and therefore their multiplicities, their presence in the unit cell in different number of counts than the molecules on general positions. So if you just reconstruct all molecules with using just atoms you need, you have a wrong composition. So we, quite a while ago, published an algorithm where you can, well, we actually used a little bit of group theory to find the symmetries of the molecule. Then we factorized the crystal symmetry group by the symmetry group of the molecule, and then find cosets and then take a symmetry operator from each coset and then apply to those molecules to which these operators were not yet applied. And this works, and we can now reconstruct the correct stoichiometric ratios of the molecules, and now the contents matches, and we have all molecules that are present in the crystal in correct ratios. But of course, if we want to have all interactions inside the unit cell, then we need to take into account that this stoichiometrically correct formation is present multiple times. So we want to reconstruct the whole P1 cell. And again, we can choose what is our molecular unit then, and have correct and composition that coincides with what authors have reported. Here, the Z, the number of units in the molecular units in the unit cell is increased by 2, 4 instead of 8, so that we don't have this non-integer coefficients. Okay, so now we apply this to the whole crystallography open database, wishing to find what molecules are there, what are their chemical and physical properties, what are the interactions. And not very surprisingly, we find quite a lot of code records that are not finite molecules. They describe nets of covalently connected atoms that span infinitely in 1, 2, or even 3 directions. Here we have example of one of this boron nitride, actually, which forms these infinite 2-dimensional layers similar to graphite. So the question arises how we describe this. And until recently, we didn't have good software to do this. So Yaroslav Rozdobudko did his master thesis, and he developed a software that allows us to construct quotient graphs from these infinite nets. Now, I didn't put in definition of the quotient graph. I probably should have done this, but I will try to spell it out. So the quotient graph is a graph that has a mapping to the original one, and a vertex in the quotient graph maps to possibly multiple vertices in the original one in such a way that whenever there is an edge in a quotient graph, we have also an edge in between the corresponding mapped atoms. So basically, as crystallographer, I think of all these boron atoms, pink atoms, as equivalent. They are the same equivalence class, and this B represents all of them at once. Okay, this is a standard way how we describe crystals in the unit cell. Of course, we need to keep the information that some bonds go out of the original unit cell and go into the next unit cell. If we don't keep that information, we will be confused and we will think that this is just a finite molecule when in fact it is not. therefore, these edges become oriented and they get special decorations. Some people call them voltages. For me, voltage is something you measure in a socket. I'm a radio amateur, so we usually say it's translations, but maybe voltages will stay. And so now we have a finite description of the infinite net, and we can start processing them pretty much the same way as we process the remaining finite molecules. For example, we can ask what is the stoichiometric ratio between this. It's interested from the chemical perspective. But this, of course, and Yaroslav is now building a database, which we plan to publish soon, but it's online already, of all nets which he managed to find in the crystallography database. So here in this interface, you can search for certain parameters. You see whether your net is one-dimensional, two-dimensional, or three-dimensional. We determine this by just taking translation vectors to all atoms in the net and then finding the rank of the matrix. And we can also find multiple nets if they are not covalently connected. And then we can ask a simple question. When you put all vectors together, will the dimensionality of the space increase or will it stay the same? And if it increases, we do a conclusion that these are interleaving nets because they live in linearly independent subspaces of the three-dimensional space. So you can have this classification as well. Very simple, but hopefully useful. And then you can go to each individual molecule, and we use JSMAL applet here to display three-dimensional structure and also to expand its quotient graph on request. And here we have a quotient graph in a schematic representation, and clicking on one atom would show you which atoms are correspond to it on the 3D image. And you have this for all independent molecular entities. Okay, so but of course, the world of infinite nets, it's much more complicated than we have just analyzed. So I think, and I mean, correct me if I'm wrong, I really would love to hear comments, objections from this very qualified audience. But I think what we can distinguish the interpenetrating multidimensional networks, a situation like here on the left, from the situations on the right, whether it's just a braid, stays one-dimensional, or they're polycatenated and become essentially two-dimensional. But we have at the moment no good tool, and we are reading the papers and trying to improve our understanding of this, but we don't have tool at hand to distinguish, to identify such situation or such situation, or let's say two-dimensional nets that go through each other like in the textile fabric. Okay. So this naturally brings us to the question, what theories could we apply to investigate such situations? And naturally start thinking about knot theory and knot. And this is, for us, interesting in the context of infinite nets. But then, of course, the immediate question arises, are there not molecules in the crystallography open database? And a quick search says, yes, there are. So this is a very nice example of a trefoil knot. Okay, and as you see, it has three identical parts, and then this loop goes over here, then under the companion string, then again upwards over here, under the previous bridge, over here, and then it goes under the last molecular bond set and goes back into the original. So chemists synthesize this deliberately. It's interesting whether there are some knots in natural compounds that went unnoticed. Probably not. Chemists are attentive, but you never know. So we would like to have automated means to discover and catalog these knotted molecules as well. So this is actually what Yaroslav is currently doing, and our plan is to follow the route which we started with the beginning of which I presented in the previous slides. So we reconstruct molecular entities. Then we convert them to 3D graphs. So to graphs, to unions of aligned segments embedded in three-dimensional space. We trim branches, we fill small rings which we know cannot have any entities going through them, like benzene rings or small rings. And then we essentially have multiple lines in the 3D space. And then we convert this to we think that we will convert this to linear representation. Maybe it's Gauss notation or Docker notation. Maybe it's a braid word, but you said it's not unique, so we'll have to deal with that. And then the idea is, so here as a software, from the software design perspective, I would like to have a standardized output. And the word standard comes out already multiple times in my talk. I think it's important that in science we have well standardized, well readable outputs. So if we have that, then I can feed our molecule representation into any of the existing knot theory packages, and then calculate knot invariants, check whether they are unknots, check whether they are we have links, anything. And then, of course, we would like to make a searchable database of this. Now, of course, a problem here is that, to my knowledge, there is no knot invariant that would be complete, right? So there could be that we get the same knot invariant and the knots are still different, okay?
There are complete invariants, but they're slow to compute, exponential time.
Okay, so, but which one would be that?
So, for example, Alexey Lisitsyn was yesterday describing such invariants.
You mean the one with algebraic invariants? Yeah, that's what I would consider using. That's very, very interesting. But does it work for any crossing number, even exponentially? Okay, that's interesting. I didn't know this.
But it's slow.
Okay. Cool. So our idea is that we're actually dealing not with generic knots, not even with tame knots, okay, the ones that has no mathematical special points, but we are dealing with the knots that occur naturally in nature. And these are limited by the sizes of atoms, lengths of bonds, sizes of molecules. And this means that we cannot have very many crossings in them. I cannot imagine a molecule with 1,000 crossings in a knot. Well, that would be a very exotic feature. In fact, actually, we have to look into that. Maybe somebody knows that. But as far as I remember, there is a theorem that says if you have line segments joined together end to end and forming a closed loop, then to make a certain crossing number, you need some minimal number of line segments. So if we calculate that we have less than this number of segments in our molecule, which we usually do, we can conclude that the crossing number is not larger than a certain number. And then possibly, yeah, well, from yesterday's lecture, I already know that this is true. So if we limit the crossing number, then we can have a complete invariant for this particular set of molecules, okay, with crossing them. Okay, and so that was our strategy, and yeah, I'm very glad that I came here because I learned that this this is true. I mean, that's why I come to conferences to learn. And so this is our strategy. Now, if we have these invariants, it could be one complete invariant or multiple ones, but we can put them into a database, and we can just present it to everybody and search and see how this correlates with physical properties. And sure it will, because if you have catenane, then disintegrating such crystal needs breakings of covalent bonds, and that's completely different from splitting away graphite layers. And now back to the nets. So with the quotient graph description, we have description of infinite nets, which are very similar to finite molecules. And to me, this hints that descriptions of infinite nets could be treated in a similar way as descriptions of knots. However, these are infinite, okay? So how do we approach that? Well, all these lines end with question marks because these are just ideas, and again, if you could comment on that, I would be enormously grateful to you. Our ideas is that maybe we can treat these edges of the quotient graph that go into a neighboring cell, which have directionality and voltage, as virtual crossings, as yes. Or what I said, Yaroslav, 2 weeks ago, just assume that you have no crossings there. They cannot cross. And then in some cases, we know that this is so you will be right. In some cases, well, maybe you make a mistake, but we'll see how far we can go technically. Another idea is that if we think of knots as line embeddings into a 3D sphere, then we can also think about infinite three-dimensional crystal as a 3 torus. So we have, let's say, a cubic cell, and then the left side is identified with the right one, the top with the bottom, and the front with the back. Okay. If it were just a square, we would have a regular 2 torus, right? And here we have a 3 torus. Why not asking about knots, whether there can be knots in 3 torus? And here I'm completely lost. I can't even imagine that. But maybe some of you knows theorems, papers, publications. Maybe David Gilbert did everything that in 1900. I don't know. But the idea sounds plausible, and that would be very interesting to pursue this structure. And then we can, of course, artificially close the quotient graph edges, like you did with proteins, right? Maybe this. And what we are after, of course, is to get a representation, a model of our net that correlates with physical-chemical properties. So my intuitive understanding is that if I have layers parallel to each other and not entangled, then I can separate them easily. Material exfoliates. It has, planes on which it can split as a crystal and so on and so forth. But if we have entanglement, then to split those layers, you need to break covalent bonds, and this is much more energy. This is completely different chemistry. So material will have completely different properties, like, graphite and diamond. And that would be interesting, I think, for material design and in property investigation. And then, of course, as said, we do a lot of software ourselves, and there are a lot of discussions. We had some yesterday. I have them all the time with my colleagues and other. So how should scientific software be constructed? And I always think that software is not just a tool, like a hammer to hit a nail, to do some computations. software is a description of procedure that we used to come to scientific conclusions. Okay, and it's a procedure described in a strict mathematical language. So if our papers on paper give a human-oriented but vague and not necessarily precise description of what we have done, then the software code just puts all dots on I's and it says exactly what has been done. And it turns out that what has been done is not always what people thought they have done. Okay, this is a different topic, but we all know things happen, bugs creep in, and so we want a readable software. That's of paramount importance for computations, for science. And then, of course, if I did an experiment 5 years ago, I want to be able to reproduce it. Okay, if I did it 10 years ago, well, probably it's still important to see that, you know, the new data set gives different results, not because software is different, but because we have something new in the data. So we want to have stable roadmap so that our software is runnable at least, well, I want to be conservative, at least 10 years. I would like to put in 50 or 100, but we never know what will be. And to understand it, we want well-defined semantics. Ideally, it should be an ISO or ECMA standard, or at least a good documentation. Well, it should have independent implementations. Like, you know why we have AMD and Intel? How come Intel gave their most valuable intellectual property to AMD, who were no one at the time when they started? And the story is, IBM said, we only buy your chips for our personal PCXT if you ensure at least 2 independent vendors. And so they licensed their x86 CPU layout to Advanced Micro Devices, a small unknown company in Germany at that time, okay? So we want the same. We're not IBM, of course, but we would like to have. And we want a high-level language, we want high-level abstractions, so that we not think about only bits and bytes, but we think about molecules, knots, invariants, polynomials, and those. And you know, we are now in the 21st century. We have all these language models. I took this list, plugged into ChatGPT, and I was pretty surprised by what came out. Well, not entirely, by what came out of the list. And this is the list of the 10 most suitable languages. Okay, so Python is on the list, but it's 10. And the first comes Ada. Mu is a well-forgotten old. It was designed for avionics and for high reliability, high stake environments, high reliability software. Fortran, what was totally unexpected to me is to see OCaml on the 3rd place. But you see, 1, 2, 3, 4 functional languages are leading the list. So I'll definitely start learning more Haskell after this. And yes, functional languages do have the appeal in that they're way more easy, as I understand, to verify. You can prove theorems. And then we have C++, which is a sort of okay, but you know, if you go to NSA recommendation, National Security Agencies, they say C++ is not memory safe. Expect segfaults. Ada is. C is not memory safe. And then you have newcomers like Rust and Julia and Python. Yes, it's popular and R, but you know, no standard, no roadmap, changes every now and when, very often. Try to run 10-year-old Python code. Oh yes, we had to. No, we had to not put brace. Whatever. So. And the explanation was also why Ada wins: long-term reproducibility, conservative evolution. That indeed, people who develop that, they think explicitly will the feature which we introduce break the old programs? Let's not rush with, I don't know, object orientation or list comprehension or yields of functionality. Let's think how will it weave into the previous design pattern. So yes, there are some unusual decisions taken in this language, but overall it has very good compatibility. So it values your work. It values our work. That's what I appreciate a lot. Absolutely readable. I give it to students, explain the algorithm, we discuss it, and ask, do you know what language it's written in? So it's pseudocode. Okay, good. But it has a compiler. It's precise and completely defined, and we have at least 2 independent compilers. Actually, we have quite a lot. Yeah, that's a text generated mostly by ChatGPT, which I interpret as this is what people on the net were writing and discussing. This is the zeitgeist, okay? Because these words are probable in the context that we have just discussed. So let's think about it. And yeah, just to finish my talk, just a couple of examples of other. This we do with our students. You can define a type, which is your vector, and then define operations, which you spell out explicitly. And then you keep working with these operations. For example, this is how we calculate dihedral angles. Okay. And of course, you will say, well, should I every time code a dihedral angle calculation? No, unless you're a student who wants to learn. But then you just see the formulas, and they have one-to-one correspondence to actually high-level already definitions. This is a scalar product. This is a cross product. Okay, this is all automated, and then you pack it into a package. Okay, this is a different package for decoding the whole, and you have one function that takes the strings and gives you symmetry operators, and you work on this high abstraction level. And another thing is we apply this, we run this on the whole PDB. Now, in one run, this is the whole PDB, okay? And this small program can calculate all dihedral angles. And, you know, add is nasty. It just crashes. It says your arguments are wrong. Okay. And why so? Other numeric exceptions are raised. And that's because there are exactly 2 cases in the PDB where you have C alpha atoms aligned straightly in one line. And then, of course, the dihedral is undefined, and other tells you that. All other systems give not a number, it's buried in a million output values. Well, I mean, is bioinformatics so important that we spend half a day on figuring out what's going on here? In this case, probably not, but I was told by my colleagues some other story. They were reconstructing genomes, and this was in medical setting where you had to decide on a therapy, actually for infants, and having a specific mutation would indicate the absolute need of medical intervention at young age. Otherwise, you know, get impaired for your life. And everything went fine. Nobody had a disease until they realized that half of the chromosomes were not assembled because they ran out of disk space. And luckily, the necessary chromosome was in the assembled set, and no one indeed had a disease. So no problems. But you see how close the call was. And I think we should start treating scientific programming, bioinformatics programming, a little bit like, you know, high-stake environment. I mean, we are responsible for what we calculate. And we are now trying with students, with my colleagues, ADA, for 3 years now. And yeah, these are some other examples. And just if you go to my GitHub repository, you can see several examples of scientific programs. And by the way, yes, if you wonder which system Yaroslav used to produce this web application, it's ADA web application. Works fine. He was working on C# as professional. He tried Rust, then he's tried Ada, say, okay, let's switch to Ada. It's quicker, easier, more reliable. Works fine. So, and final touch, Ada has an extension called Spark and has a tool called GNAT-proof. And you can formulate preconditions and postconditions in your programs. So, for example, if I have a function that takes ring elements, very abstract, I can define what these are. In this case, it's the arithmetic modulo 37, modulo prime number, but I can define it in another way. And now I want this to be a group. And being a group means having identity, being closed under multiplication, and have an inverse for every element. And now I can try to prove that what I have coded in there indeed does the job. And in this case, with some tricks, GNAT-proof says I could prove the cross conditions, and then I compile it and run it, and yes, indeed, it does spit out the necessary group elements. So I would love to have, validated, verified library for basic crystallographic algorithms, maybe mathematical algorithms, knot theory algorithms, you name it. So to conclude, I think we've seen COD is a useful resource for direct chemical data. You are welcome to use it as well. It can serve as a hub of linked data and derived data. And it has a noticeable part of entangled nets. Not so many knots, but we don't know exactly how many. And this can and should be detected automatically. And then my last pet conclusions are scientific software should be readable, should be verifiable, and one of the tools is Ada and Spark. And I thank you for your attention. The slides will be shared. They have all references and everything is clickable. Thank you. And if there are any questions, I would like that.
Thank you. Thank you for listening. We'll stop the recording and